All right. Hello, everyone. Welcome back to another Physics Meets ML. It is wonderful to have Anna Golubeva from the Perimeter Institute and the University of Waterloo giving today's talk, Wide and Sparse, about the interplay between wide and sparse neural networks and how those things play off of each other. This is based on some work with some folks at Google. And her background's in condensed matter physics, but she also has some pure AI work, which we're going to hear about today. And we're also pleased that she's going to be joining the NSF Institute for Artificial Intelligence and Fundamental Interactions as an I5 fellow in the fall. So that's something I'm a part of, and we're excited to have you join us. So today we'll hear about your work, and we're excited about that. So please take it away.
Thank you very much. Thanks for the introduction. I was very excited. So yes, I'm going to talk about wide and sparse networks. They are at the center of attention in this work, in this study, in which we asked, are wider nets better given the same number of parameters? So this was done with people from Blueshift, Guy Gurari and Behnam Neishabur. Blueshift is also part or affiliated with Google, and I was an intern there. Okay, so just a moment, my navigation is not working here. All right, now it does. So the motivation to ask this question is very intuitive. We know empirically that increasing the number of neural network parameters improves performance. So for instance, take a look at this graph. It shows the performance on ImageNet as a function of number of parameters and puts several of them state-of-the-art deep learning architectures on the curve. And in general, we see the trends. The better the model performs, the more parameters it will have. So now the second piece of empirical observation that we have is that typically the number of parameters is increased along with layer width. So when the model is bigger, it will have wider layers and more parameters. So the natural question to ask is the performance gain that we are observing here. Is this because of more parameters, or can it be attributed to the larger width? So that's the original question that we want to study. And for this, we need to find the way to decouple parameters from the width. This is not at all straightforward. So we thought about methods to achieve this. So we came up with 3 methods. 2 of them are called the bottleneck methods. They operate on the level of layers. So it's a trade-off. We increase some layer width. So overall, we refer to the model width as, or like we say that model width is defined by the width of the largest layer, of the widest layer, right? So we could increase some layer dimensions, some widths, at the cost of some other dimensions. So we need to squeeze another layer dimension in return. So this is what creates a bottleneck in the architecture. So let's focus on the linear nonlinear bottleneck for now, and then consider the third method, which is the sparsity. So in case of the linear bottleneck, this is an illustration which just shows the basic principle. We split every layer in the network in 2. So essentially, it is a reparameterization where we replace a layer matrix W, a weight matrix W, by a product of W1 times W2. And then we reshape these matrices such that the middle dimension, which we call the bottleneck dimension, is very small. And with that, we have some space to increase the input and the output, like the incoming and the outgoing dimension of these 2 layers. And note here, when we split the layers, we do not add an activation function. So the red line in the scheme indicates an activation function, such as a ReLU, for instance. So in case of the linear bottleneck, there is no additional activation function. Now, the problem with this method is it changes the depth of the network. And this is a major architectural change that we introduce, which we would prefer not to have. And what we have found in experiments is that this reparameterization strongly affects the trainability of the model. So it's really hard to compare a modified model to the baseline that we started with. So the nonlinear bottleneck might be another option, we thought. Here we modify layers and pairs. The principle is the same, But instead of splitting a layer in two, we grab a pair of layers and then squeeze the middle dimension, increase the outer, the incoming and the outgoing dimension. The problem with this method is it leads to worse performance. Or I should rather say it's not a problem with the method, but this is what we found as a result. So if we apply this method, performance tends to just monotonically decrease. Why we did not like the method itself is that there is, again, like there are many limitations that come with this structural architectural change. There's only so much that some middle dimension can be squeezed, and it only allows for, only gives room for a width increase that is just limited. And so we actually focused on the third method, which is the static sparsity. So this is the scheme. This is representing the principle. In this case, we do not operate on the level of layers, but on the level of individual weights. So all additional, when we increase a layer width or network width, the additional weights that come in, we need to be, well, we need to compensate for the additional weights that came in by removing some of them, not necessarily the new ones. So we do this with a sparsity mask. The sparsity pattern that we apply is random. It is applied at initialization, and it remains static. That is, it doesn't change throughout training of the neural network. Now, important questions to ask are, how exactly is the sparsity distributed? Now, the per layer distribution is done according to layer size, as indicated here in this little example. So imagine we have a neural network with 4 layers. We count the weights in each of them and sort them according to their size. And then say we have to remove 9 weights. We would start removing weights from the largest layer until it reaches the size of the next smaller one. Then if we still need to remove weights, we continue removing from all layers of the same size, and so on until we have distributed all 9 weights that we need to remove in the network. So that's the basic principle. The rationale behind this principle is that we do not want to harm, like to sparsify small layers over proportionally, because typically in the neural network architectures, layers can have very different size. And if we were removing a fraction of weights from each, it could still lead to the situation where the smallest layer is just completely cut out, and that would just basically like cut a neural network in two, so it wouldn't work. Okay, the next question to ask is how to distribute sparsity within each layer, because a layer is corresponds to a weight tensor, a multidimensional tensor, simple, fully connected feed-forward network, layers that have 2 dimensions, input-output. But when you think about convolutional layers, they have 4 dimensions, because additionally to input-output, they have the 2 kernel dimensions, as in the width and the height of the kernel. And so our approach is to distribute sparsity uniformly across all layer dimensions. This is the simplest one. We do not put any restrictions on like how many weights are removed from each individual neuron. We just do this at random, and we do not monitor whether individual neurons are being cut out or not. That could potentially happen at very strong sparsities. Okay, so the advantage of this method compared to the bottleneck methods is that this one does not alter the neural network architecture. And as such, it is also very easy to adjust and generalize to different architectural, like neural network architectures and layer types. And one important point that I want to stress here is also that the sparsity that we are applying is really not meant to optimize the network performance. It is something that many people tend to make this association because there is a very popular and very interesting field of research in neural network sparsity, where the sparsity is actually optimized to the network, and the goal is to find a sparsity pattern that works best. So in our case, this is not the objective. We just need a method to detach the number of parameters, like basically this 2 knobs experimental knobs that tune the network, the number of parameters and the width. And sparsity is our way to make them separate. Okay, so let me summarize our approach to the experimental study. So we select a model type and architecture, which specifies what kind of layers we have and their arrangement. So for instance, we could say we take a ResNet 18, which is actually it was the main workhorse for the experiments in this work. And then we say it's going to have like 32 output channels in the first convolutional layer. And by that, all the remaining architecture is fixed. And so this specifies our baseline model. So the baseline model is dense, meaning it has full connectivity, none of the weights were removed. And that defines the number of weights. So the baseline model sets the number of weights, which we fix. After that, we build a family of models derived from this baseline by making it wider and sparser accordingly, so that the number of weights is still the same. And so once we have this family of models starting from the smallest dense one and then the wider ones and progressively sparser ones, we train them and compare their performance. And the task that we focus on is the image classification task on different data sets. I see a raised hand, so please go ahead and ask a question.
Yes. Hi, Anna. I'm curious to understand more exactly what's this family of models. Because I don't understand exactly how is this model, or how is this family, or if it is connected to the linear or nonlinear bottleneck. How?
No. So we've dismissed the bottleneck methods. We check them. We consider them as possible potential methods to separate width from number of weights, but we didn't like the alterations that they introduced into the network. They were they did not provide a clean experimental setup. So we have set the bottleneck methods aside. What we focused on is just the sparsity. And so in this approach here, like in this outline, what I'm describing, the family of models means you take some model, like you choose some model, for instance, a ResNet 18 with a certain width, and it has 1 million parameters, for example, right? So this is the baseline, this is fixed. From there, we start increasing the width, which means the width of we take the width of the first convolutional layer as reference, right? So for instance, we double the width, make it 64. When we do this, there is a number of additional parameters that come into the model.
Yes.
But we still wanted to have 1 million. So 1 million parameters is our strict number of weights of parameters in the model that we cannot exceed. And so, for instance, if we double the width, and the new model will have 4 million parameters, that means we need to remove 3 millions to get it back to 1 million. And we do this by applying the sparsity mask.
Got it.
In the way that I've explained, like with all the per layer distribution and so on.
And the depth of the network is the same because you change only the right? Yeah,
exactly.
Thank you.
This is something, you're very welcome. Thanks for the question. So it's an important point to clarify, because everything else, like all the results build on this. Yes, we definitely did not want the depth of the network to be changed, because it comes with so many additional changes in the training dynamics, in like both in the optimization procedure, also in the performance, that it wouldn't allow for a really clean comparison between like model that has larger width and more weights, or which has the same width but is sparse. So this is a cleaner setup. Okay.
Can I also ask a question?
Of course.
So when you sparsify, do you make weights non-trainable, or do you mark them, or how exactly do you sparsify? It doesn't even matter. I mean, does it influence the training dynamics whether you do one versus the other?
So it's, as far as if I got it right, it's a question about the implementation of sparsity, right?
Yeah,
like
exactly. How do you make it sparse? You make it sparse by by having the weight some random initialization value, not updating it during your training, or do you just mask it out?
We mask them, we set them to 0. So it's an important technical question from the side of computational cost. Ideally, it would be ideally we would need a sparse implementation, which really has the benefit of not computing all the updates and gradients for those weights that are being zeroed out. At the time that we did these experiments, it was not possible with PyTorch. There was still the sparse API was just starting to be developed, and it was not possible to have real computational savings. But I think that it's a very active field of development. So it would be actually computationally advantageous if we would have an implementation which doesn't simply put a mask on the model, but actually defines the matrix natively as sparse.
Good. And then, so as you said, there's sort of the problem why the bottleneck layers don't work, because there's some implicit regularization if you do matrix factorization and sort of take this into two, even though sort of as on the level of an affine map, of course, these two matrices would be the same map, but then just because you made the network that deeper, you introduce some regularization. So if you if you were to sparsify by leaving the parameters in there, not masking them, but also not updating them in training, would that lead to a different result, or would it be the same as if you just mask them out? Do you know?
I think it would be different. We haven't tried. It would still mean that if the parameters are non-zero, they are contributing to the network function, right?
Yes, but eventually there would be just a constant which probably could be mirrored by a bias in the last layer. But again, as I said, so just because it can be expressed as an affine map, in the end, it doesn't mean that that the training dynamic stays the same. But so you haven't.
That's true. There is no, we haven't looked into that, but also one remark about this reparameterization when we split one matrix into two. The bottleneck dimension that we introduced, it's essentially a low rank constraint on the matrix, on the original matrix, right? So this is an additional change that comes in that definitely has an effect on the training dynamics.
Okay, thank you very much. There's another question. I'm done, thank you.
Okay.
Thanks. I'm sorry. I was just going to ask, would it have been possible, or might it be interesting to imagine a slightly different experiment where instead of controlling the number of parameters by introducing sparsity, you actually use the number of layers to do that? For example, you can imagine a two-dimensional table where we have widths along one axis and number of layers along the other. And you can compute the performance for every cell in that table, and there'd be a manifold of constant number of parameters going through that table, and you'd be able to see how the performance varies as a function of those two independent variables.
Definitely possible. Essentially, what you're saying is looking into the depth as another axis
as a way to control the number of parameters. Yeah.
Yes, it is possible. Comes with a lot more complications because of the trainability. First of all, we cannot indefinitely increase the depth, because every additional layer would also mean that there might be a gradient vanishing problem, or would probably require additional regularization. So we did not go in that direction. But I know a work that is appeared right after ours. I'm going to link it later in a chat, which actually looks into this question. It does consider the depth. They have pretty cool results.
Great, thank you.
You're welcome. Okay, so let's get back to the approach. So I have one additional comment here about the ResNet 18. Since we are looking, since we're considering this model, it's worth taking a closer look at this and explain what exactly we're modifying there. So what you see is a scheme of a ResNet 18, just lying down. Input is from the left, output on the right. A ResNet 18 contains of the first convolutional layer, then followed by 4 blocks of 4 convolutional layers each. And the last one is a fully connected layer at the very end. And these blocks, they have a fixed width ratio. So these numbers here, 1, 2, 4, and 8, they refer to the width ratio of the blocks relative to the first convolutional layer. So when we talk about model width or the base width, like when we're setting the baseline model and choose the model width, in general for the ResNet 18, we refer to the number of output channels in the first convolutional layer. It's technically not the model width, but because the subsequent layers are just defined by the width of the first one, it's just as good of as a reference, right? We just pick that one. And so we do not mess with this ratio of widths, the 1, 2, 4, 8. So let's take a look at the results. So here's the first plot showing an overview of results that we obtained with the ResNet 18 on 4 different data sets, SVHN, the CFARS, and ImageNet. And we have the test accuracy plotted versus the widening factor. Now, the color corresponds to the data set. The model size is indicated by the marker shape. So we did have 3 different sizes of the models just to adjust to the difficulty of the data set. So on ImageNet, we had something like with 12 million parameters. And for the other data sets, it was less than a million because they're much smaller. But generally, what we see for all data sets is that the performance improves as the width increases, even though the number of parameters stays the same in all of these cases. However, up to a certain width. So when you look at the curve for CFAR 100, for instance, right, we see that there is a maximum for all of them, but there is a maximum at a certain point, and then the test accuracy starts decreasing again. Okay, so in the next plots, we take a closer look at the experiment results for the smaller data sets, okay, SVHN and the CFARS. Here, each data set is in its individual subplot, right? And once again, we have test accuracy versus the widening factor. And now the color and shape of the markers corresponds to the model size. So we're testing ResNet 18 models with a different number of, setting the different number of convolutional layers in the first, different number of output channels in the convolutional layer, which is the first one. So here, for instance, the smallest model has a base width 8, and the largest one has a base width of 64. Now, what we see here is that the improvement that we observe with widening is strongest for smaller models and harder tasks. So for CFAR 10, for instance, if we take the smallest model, oh, by the way, I've just noticed the recording dot disappeared. I'm not sure what it was. Maybe it just disappeared for me. Maybe it's not. Is it still recording?
It should still be fine for my recording. So
That's
okay.
recording for me as well. Yeah.
Oh, all right. That must be just my screen. Okay. So CFAR 10, consider the smallest model here. And we're just measuring the maximal possible improvement from the baseline model, which is at the widening factor of 1, which is the dense one, to the maximum, which is at the widening factor of, I'm not sure, but whatever, like we check the distance. And this is about a plus of 3.5% accuracy improvement. And then if we consider the next one, it's about 2.5% and so on, and keeps decreasing. And the same for CFAR 100, but on CFAR 100, you can see that the improvement in percent is even larger than we saw for CFAR 10. So it has about plus 6% and plus 5% for the smaller ones.
Can I ask a question?
Of course, yeah.
It's interesting because you are saying that the improvement is strongest for smaller models and harder tasks. And they seem to be at different parts of the spectrum. Like typically you use small models for simple tasks, big models for harder tasks. But now we seem to talk like about both sides of the spectrum as like even small, because for harder tasks, we need bigger models, no? And
that's right, but these two have to be seen in relation, I think. Like the size of the model is like relative to the hardness of the task, right?
Sure.
Because like if I take a model which is too small, or for instance, if you look at the very large models in these plots, which have like base width 64, the orange and yellowish ones, right? There is barely any, like one can see probably some improvement, but overall, like the curve is pretty flat. Because it's already maxed out. Like this model is pretty large for the given data set, and there are just some limitations that apparently do not have anything to do with the number of parameters anymore. It's just due to the architecture itself, where
So
it's already maxed out.
If I misunderstand, are you putting an and? Like, is this improvement seen when it is both a small model and a hard task? It's not like an or in between them, right? You're saying like in the case when you use small models for hard tasks, good things happen. You are not making the statement just for small models in general. You're making it. Are you making the statement for small models on hard tasks specifically?
I wouldn't say so. No, I would consider the statement for a given task first. And for a given task, we observe that if the model is smaller, then the benefit from the static sparsity and widening is going to be even bigger. And as the model is increases, like the size of the model overall increases, then the improvement gain through widening is going to be not as much. One could argue that it's natural because when you start with a very small model, for instance, the one with base width 8, right, and CFAR 10, then, well, it does like 88 something percent, 88.5. It's just limited, right, by the question is by the width or by the number of parameters, right? One starts increasing the width while keeping the number of parameters the same. The model does better up to a certain point, right? But we see we can gain an improvement of 3.5% while the number of parameters is actually still fixed. So that's like the first observation. Now the question is, okay, if we started out with a larger model initially, which has more parameters, how much improvement would we get there? And we see that then the improvement is smaller, like in just absolute in percent. It's only like 2.5 for the next larger one, right? So this is like one part of the statement. This is like the comparing the size of the models, and then comparing between data sets. There we have models of the same size on different on tasks of different difficulty, CFAR 10 versus CFAR 100. And if we compare the model of like approximately the same size, well, the like 1.8 times 10 to the power 5, right? The base with 8. Then we would see that the improvement on CFAR 100 is just in absolute value, like the delta in percent is bigger. We get a 6% improvement.
Got it. I think things are much clearer now. Thank you.
Okay. So here is ResNet 18 on ImageNet. Yeah, sorry, is the question?
More questions in chat. Yeah, I also have a question, but maybe you just, I don't know whether you want to take them now or later, but I just wanted to draw your attention to the fact that they're
thanks. Yeah, no, I'm also noticing the chat. Yeah, please, if you could unmute yourself, because it's inconvenient for me to open chat and read, so just go ahead.
Hi, I have a question about why the performance. Do you know why the performance is going worse once you keep widening after a certain range?
Yeah. So this is an important question, and I'll get to that. It is related to the trainability, training performance, but I'll talk about this in more detail in a couple slides.
Okay, thank you.
My question was, how do you know the performance is changing because of the widening of the networks and not because maybe you have a different initialization? Or, I mean, even if you keep the number of parameters the same, something is going to change slightly, and that could affect the change in performance. So how do you know that happens? Because how are you sure that that happens because of the widening of the networks?
So we did our best to exclude possible confounding factors in this case. It's true that the initialization might play a small role, but we did, like for instance, on ImageNet, it's harder, of course, because the experiments are so expensive. But for the smaller models, we did multiple runs, like 5 or 10 random seeds, and plotted like the results with error bars. And there is not a significant change. In essence, like I do not have plots with error bars in here, but they're about the marker size. So there is some variation, but not much. So the effect is definitely stable with respect to initialization. And this is, in fact, the only factor that we could think of that could also be contributing to the change. Other than that, at least from the obvious ones, we have the width, we have the number of parameters that we control, and everything else is actually staying the same. But would be definitely curious to hear, and it's a very valid question to ask, because it's like the whole experimental setup. This is why it is hard, because everything is so interconnected. And in order to answer the question that we posed cleanly, we do need to make sure that we do not have additional variables changing while we are adjusting one or the other parameter.
Can I ask a question?
Yeah.
So the way, if I understand correctly, the way that you implemented the sparsity constraint, sort of, it means the probability that a given weight is going to be set to 0 is much higher for a very large layer. So for one of the later layers in ResNet 18, as opposed to one of the earlier layers. What happens if you just sort of don't, you just sort of treat all the layers equally, and so that any given weight's probability of being set to 0 is independent of which layer it's in? Because you might worry that what you're doing now is kind of treating different layers differently. And so when you are making when you're saying that you're making it sparser, you're treating the layers differently and you're treating the weights differently. So I'm curious what happens if you sort of treat all of the weights democratically.
We did not try this with the ResNet, as far as I remember. We did this on smaller models and the fully connected MLP with multiple layers that we were experimenting it like for various, to check like the initial setup. And so there, the problem that we run into is basically that the smaller layer is just harmed over proportionally through sparsifying, and the model just doesn't train as well. Like at some point, there are just too few connections somewhere, and that just.
Because one of the things that I noticed on your previous slide is that there's a turnover when the sparsity factor was around 8 or so, or when the scaling factor was around 8, which at the very least for the models that, the networks you're considering now means that the early 4 layers in your network are not being sparsified at all, right? When the width factor is less than 8. So I was wondering if that factor of 8 had anything to do with the fact that there was some feature in your graphs at around a width factor of 8.
That's actually
just a coincidence.
Interesting question. I would look into this. Let me just take a note. I haven't looked into this closely. Probably. So I have a couple of plots that I think I haven't included them into the presentation, but at the end I can just open the figure and we can take a look. They show ResNet 18 at different sparsity levels. And there we can see exactly how like in percentage, how much is every layer, how much has it been sparsified. I'm not sure that there is such a threshold.
Well, we can chat about it maybe at the end. But I don't want to distract you.
Definitely.
Thank you.
This is kind of a follow-on to that. Is the lottery ticket method / hypothesis relevant here?
It is related, but a different direction. So the lottery ticket method and the whole like field associated with that is working on finding a sparsity pattern that would be optimal. So there are methods that really optimize the sparsity pattern based on some network features. And the main problem essentially is that it's hard to derive the optimal sparsity pattern for a network that that is at initialization that hasn't been trained yet. When the network is already trained, then it's pretty easy. Then even like magnitude-based sparsity is actually very beneficial and leads to very good results. But so there, the question is, how do we optimize the sparsity pattern to achieve the best performance? In our case, the question was really not about optimizing the performance in terms of sparsity. Sparsity was just a method, but it just turned out to be, it has a lot of association, of course, with the fact that we know that sparsifying neural networks can actually improve performance if done right. But in our case, we intentionally keep it just as simple as possible. We do not optimize it. We are not looking at bumping up performance of the neural network through the sparsity.
I also have one more question. It's more,
Okay.
It's about what Carlos was asking more or less. So in the plots in the previous slide, how did you decide when to stop training? I mean, for example, because when you sparsify the way you do and you initialize, for example, Xavier initialization, then the size of the weights is set usually by the size of the input and the output dimension. Now, if you mask half of the input and output dimension, you should have changed the variance of the initialization of the weights.
We do adjust that for the initialization. So definitely in the standard initialization, the variance of the weights are drawn from a normal distribution with variance that is usually like 1/square root of fan in.
Exactly.
And fan in, right, is the number of incoming connections. So if we make the network sparse, then we would have less incoming connections. Now it's different, like it's not uniform for every single neuron. And we do not compute it exactly, but we just take an average. Like we multiply this fan in by the sparsity factor to factor in the on average smaller connectivity.
Good. And then you just train them all for the same amount of epochs?
Yes, we do. Well, we select the best result. The results, like for test accuracy that we're showing, are the best attained test accuracy. We did experiment with how much training they need, but like there was a choice, right? Like to do early stopping, or essentially it's like train for a fixed number of epochs where we know that it's not improving anymore. And then from there, we just pick the result, which was the best achieved test accuracy, not the final one.
Okay,
because there might be fluctuations, right?
So what about the other hyperparameters in training? Like, would there be any correlations between the width and those hyperparameters?
So for these experiments, we have not adjusted, we have not tuned the hyperparameters for individual networks. We chose the hyperparameters for the baseline model, like the ResNet 18, the dense one, and we also chose, well, essentially they do not vary that much for different widths, at least in the range that we have considered. And so we keep those hyperparameters fixed, even like for the sparse ones. We do not readjust them.
Could I ask how many times do you repeat your experiment?
We did about 10 runs on the smaller data sets, and for ImageNet, we just checked for 2 experiments that we checked the variance that we obtained. So we repeated, I think, with 90 and with 128 twice, but that was it, because like the A run for ImageNet with the ResNet 18 like that would take like 3 days. So there we were limited by the compute budget.
I have a question. So does the sparsity not become a confounding factor for your results?
In which sense?
I mean, like, so you say you randomly initialize a sparsity mask, or will you also increase the width and you do your static sparsity thing? But then does sparsity not become a confounding factor? Like when you run your experiments multiple times, do you keep the same static sparsity mask, or do you also change the sparsity mask for each trial?
We change the sparsity mask. So for each reinitialization, so if we repeat the experiment for 10 random seeds, then it would be also like 10 random seeds for the sparsity.
All right.
For the sparsity mask, yes, exactly, like for different initialization. So we do, well, no, that's not, yeah, so that's the thing. So when we do like random seeds, then the mask is also initialized randomly. It's a new one, it's not the same.
All right, thank you.
All right. So back to ImageNet. In this table here, we have summarized the results that we obtained for the experiments on ImageNet. And here we did two, like we've considered two different, well, say model families. So the sparse ones, they all have 11.7 million of weights. The dense are the dense counterparts to every sparse model. That is, they have the same width, but no weights have been removed from that model. And the interesting result here is that, for instance, consider width 90, the sparse model can perform better than the dense one even. We have 69.56 for the sparse one and 69.11 for the dense one, where like for ImageNet, it's a significant difference. And again, what we observe here in general is that the improvement that we obtain with increasing width for the sparse models is actually on par with dense models, with the caveat that it only works up to a certain maximal width, where you see that, well, around here 181, there the sparse is already significantly worse, and then the gaps keeps increasing as we increase the width. So an important question that was also brought up earlier is, what is this certain maximal width? And also, how can we actually quantify this difference that we observe here between dense and sparse? And so this is what we do in the next slide. We compare the performance increase for wide and sparse versus wide and dense models. Now, these plots show the explained improvement versus the widening factor. Explained improvement is defined as the delta in test accuracy that we observe for a sparse model and the delta in test accuracy for the dense one. So the way you can think about it, this improvement that we observe for the dense one is the improvement due to width and weights, whereas the improvement that we observe for the sparse model is due to width, because we haven't added weights. Now, when we divide these deltas, basically we compute the fraction of improvement that was contributed or can be attributed to the width alone and not to the weights. So this is what is plotted here in black triangles. And you can see as the widening factor increases, the fraction of explained improvement decreases monotonically. And here, the horizontal line, the gray line, just marks the 50% threshold. So we say that as long as this fraction is above 50%, that means most of the improvement that we observe can be attributed to the width. Now consider the right y-axis, the training accuracy. So this is the red data points here, red circles. First of all, we observed that the shape is like, it's the same concave shape that we have seen in the test accuracy. That means up to a certain widening point, the training accuracy increases, and then it starts decreasing again. And these vertical dashed lines indicate the maximum of the training accuracy. So that means that after this particular widening factor of around 7, 8, I guess, in case of CFAR10, the training accuracy starts declining, starts reducing. That means the model is sparse, is too sparse to be perfectly trainable. So the sparsity starts to impact the training ability of the model. And now, why we plot this together is that there is an interesting correlation that you can observe if you consider the black triangles and the 50% line. You can see that the explained improvement drops below this threshold of 50% around the point where the training accuracy starts decreasing. So the conclusion that we draw here is that as long as the model can achieve a high training accuracy, most of the improvement in performance can be attributed to the width. Once the sparsity becomes too strong, the model doesn't train well. And then obviously like this benefit of width doesn't play a role anymore, because width without weights doesn't allow us to train, right? Like we could be increasing the width, but if we don't add weights, model cannot train. Okay, so now I get to the second part. Yeah.
Can I ask one question about that slide?
Of course.
In the slide on the far right, one of the black triangles is above 1.
Yeah, that's
What's
for
going
ImageNet.
on?
So that's here in the table, the point that I've highlighted before. At width 90, we have the situation where the sparse is actually doing better than the dense one.
Yeah, I see.
So yeah, that's unfortunate for the definition of like explain improvement, but
okay.
Yeah, that's the situation. It is at 1.4.
Yeah, okay. Okay, thank you.
Okay, so let's get to part 2, which is the theory. So we did, mainly our paper was an empirical analysis, but we have also tried to explain the effects that we have observed from a theoretical perspective with a theoretical approach. And specifically, we have considered the infinite width limit and Gaussian process kernels. There's been quite a lot of work on this in the past couple of years. Specifically, researchers have studied models in the infinite width limit and their behavior in this limit, which becomes can be captured by a kernel associated with Gaussian processes. And we thought maybe this is a suitable approach, theoretical approach, to explain the effect that we're seeing. So we had essentially 2 hypotheses. First of all, the performance improvement is correlated with the model having a Gaussian process kernel, which is closer to the infinite width kernel. And the other hypothesis is that the distance to the infinite width kernel can be reduced by increasing network width alone without adding additional weights. So these are basically the assumptions. They are mostly intuitions and, well, as the name says, hypothesis, they can be questioned, but like with this thought, we went into this analysis and decided to see what can we observe. So we computed the GP kernel for a sparse ReLU network with 1 hidden layer. So we're looking at the toy model because obviously ResNet 18 is not easy to handle theoretically, so we need to scale down. And what we found is that there is a strong correlation between model performance and the distance to the infinite width kernel, which is confirming our hypothesis. Okay, now I'll go into more theoretical results and walk you through the calculation, like roughly the setup. So the network is defined as a function mapping from the input in small d dimension to the output large D. And this is the network function. It has a prefactor alpha, which is a constant, and then the matrix V, another matrix U of weights, and the input X. And these brackets denote the ReLU activation function. So H is the Heaviside step, and alpha is the constant. And also as a note, in this case, we are considering NTK parameterization. And for those familiar with this, so alpha is like the prefactor. And then we have in the not standard, but the NTK parameterization. I was just more convenient for the calculation, for the theoretical calculation. So U and V are the parameters that we denote as collectively as theta. And now the probability distribution of the parameters, we can write it down as follows. It is a Gaussian with prefactor P plus 1 minus P times the delta function. This part with 1 minus P and the delta function accounts for the sparsity. That means with probability P, the model or a single parameter in the model is going to be drawn from a Gaussian distribution, and with probability 1 minus p, it's going to be set to 0. And so p has the interpretation of connectivity, which is 1 minus sparsity, essentially. So the Gaussian process kernel is defined like this. It is a scalar product of the gradients of the network output with respect to the last layer only, the parameters in V. And the distance from the infinite width kernel is expressed here. So it is the expectation value over the parameters theta of it is actually so we define this distance, the difference squared, the expected squared difference between the kernel for the infinite width network and the kernel for the sparse network, which has connectivity P and width N. Okay, yeah, so here the label is the infinite width kernel. And the expression for the infinite width kernel, which is dense, right? It is a closed form expression that we know. So we compute a formula, we derive a formula that approximately describes this distance. So this is what is plotted in the right plot here on the y-axis, on the left y-axis. This is the distance to the infinite width kernel. Now, the gray curve is the theoretical result that we obtain. The blue, dark blue points is the distance that we compute experimentally. So we build this small one hidden layer ReLU network. We train it on MNIST. This on the left side, the plot here is basically the experimental result. We just ensure that in the toy network, we observe the same effect. So as we increase the width, and if we keep the model dense, the performance keeps increasing until it saturates at some point. And if we actually keep the model at the same number of weights, make it sparse, then we will observe the same concave shape where we have a maximum at a certain width. So with this, it's established the same effect that we've observed in a ResNet model on large data sets is present in the toy model. So back to this plot with the distance to the infinite width kernel. Gray curve is the theory. Black points are experimentally computed distance on this network and MNIST. And we see that they coincide pretty well up to the point where we get to large widths. And there we have a deviation that we are aware of because of the approximations that we made. So when we derived the formula that describes this gray curve, there was an assumption which basically makes it such that we would expect it to see a deviation for larger widths. But for smaller ones, we do have great agreement. And what is very interesting is the correlation that we observe here with the test error. Test error is plotted in pink on the right y-axis. We see that essentially the test error traces the results for the kernel distance. And so from the theory, we get a prediction for the optimal connectivity P star, which is approximately given as the square root of NP over 4D. N is the width, P is the connectivity, and D is the input dimension. So this is an approximate expression for the optimal width and optimal connectivity. And this is also coinciding with the minimal test error that we observe in the experiment.
Anna, real quick, so optimal here for you just means minimizing the distance to the infinite width kernel?
Yes. Optimal is the minimization result. Yeah.
And it happens to correlate with low test error by your experiment?
Yes. This was like really a purely experimental result. We just wanted to compare how predictive, can we, because one of our assumptions was that this kernel distance has something to say about model performance. So that was the idea. We computed the kernel distance and then we plotted the model performance. And so in this case, it does indeed track, these quantities do coincide very well, the kernel distance and model performance. Okay, so that's it from my side. Thank you very much. And I'm excited to hear more questions.
All right. Thank you for the wonderful talk. I'm sure there are more questions. Let me take a look at the chat. There's nothing else in the chat. But,
I've got a quick
go
one,
ahead.
if I may. Can you just go back to the previous slide with the thing? There's something very obvious I'm not... Where you've got small width, then how can you be still close to the infinite width kernel?
It is to some extent, yeah. It's the question of, it's a question of like how wide does the network have to be in order to approximate the infinite width kernel? Yeah. And it just like there is no precise answer to that. Like how wide is wide enough, right? Like what counts as infinity? This is just what we find experimentally, also from the prediction, that in this case the result that we obtain. Because here in this case also for the width, so there's one little detail about this plot. The width still means that the number of parameters is fixed, right? So the model here in the beginning, the first data point is a dense model. And then we make it sparse. Like then we start increasing the width and making it sparse.
Yeah. So like a priori, there was not even a reason why the curve would have to decrease initially, because the number of parameters is being held fixed. Yeah. I mean, in your model, I understand that you did a calculation that shows that it does, but there's a calculation that you did, I assume.
That's true. Yeah, I think I do get the point now.
Anyway, that was not a question anyway, so thank you.
Okay.
Yeah, well, thanks. It's interesting. Thank you.
And is this related to once you increase the width, because the network is it related to the fact that you're doing a random mask, or is your theory hold even if you like do something like the lottery ticket hypothesis when they pick the best weights? So
no, so in this case we do assume so it really depend on the probability distribution for the weights, right? So because we are taking averages over the random initialization, right? Essentially, like this average here of a theta means that we are averaging over different initializations of the weights, and the initialization of the weights is determined by this probability distribution. And so if we were optimizing the mask, then that would change this probability distribution. Then this probability distribution wouldn't describe the weights in the model anymore. And there, I'm not sure how exactly, like possibly there are ways to encode a given sparsity mask into the probability distribution, but it would be a different one. And then the results would change accordingly.
Okay, thank you.
I would like to pull up the figure which shows a sparsity distribution in the ResNet 18 model that we talked before, where we had a question. Let me see where I can find it. Okay, just need to download. So here is the sparsity distribution for like essentially every single layer of the ResNet 18 in the order as they appear in the model is listed here on the left axis. And we have models with different widths, different sparsity levels. I should have another one as well with smaller sparsity levels. Okay, here it is. Yeah, so from here you can see how like the pattern of how the model is sparsified depending on the number of layers in the model and the model width. So the base width here, like, so all these plots refer to a model, a ResNet 18 model that has a base width of 8. And then from 8, we start increasing to 12. So the 12 has already a sparsity of 55%. This is something slightly confusing in the beginning because we would, well, I would say it's probably surprising when you think, okay, so the one that had width 8 had a certain number of weights, and then we went to width 12. Why does this already require 55% sparsity? The thing is that it seems like a small change from 8 to 12, but then all the rest of the layers, and there are many, there are 18 layers, they change accordingly. And that brings in quite a few additional weights. So that means that the sparsity is like the way the sparsity and the number of weight scales is just not linear with this width. Yeah, but this is roughly
part of the motivation for my question really was that, like, if you look at what you're doing at width 12, like you're treating the different layers very differently. Like when you're sparsifying by, you know, I guess you're sparsifying by a factor of a half or 2/3, I guess. Like overall, you're sparsifying by a factor of 3/2, but you're treating the layers very differently. And so to some extent, what you're doing is, like, if you look at width 12, the layer 4 are becoming much more similar to layer 3 in the sense that in the original ResNet model, the layer 4 had twice as many parameters as layer 3, but now they effectively have the same number of parameters almost. Right. So like the thought was that, you know, you're so kind of not treating the different layers democratically. So there's the sense in which, like, this is not a complaint, but my question maybe, is there a sense in which you're kind of modifying the architecture when you're doing the sparsifying? You see what I mean? Because, like,
yeah,
you know,
definitely, like, see, yeah,
like,
I see your point.
Layer 4 is kind of now a lot closer to layer 3 than it used to be at width 12. And finally, and you can see that, like, what might be happening is you had that accuracy turnover at around the scale factor with a widening factor of 8 or something like that. But but that seems to be at about the place where layer 1 starts being sparsified. So you might just suspect that layer 1 is doing something super important, right? And that's why your accuracy is going down. Right.
It's a very definitely very interesting remark, and you know, I'm going to check this. I haven't looked at this precisely. It is definitely a valid argument because, of course, when we start structuring sparsity, like, we found that not structuring sparsity leads to a bad setup because in that case it will happen just too early, in the sense of, if you think along the axis of width, you start increasing the width, and it just happens way too early that the model is going to be broken because something is, like, some piece is going to break off.
I mean, you could restate. I mean, maybe the point is that the whole point is to not impose sparsity democratically, because you can, like, imposing sparsity means you can get away with throwing things away. And maybe the lesson is you can't get away with throwing away things in layer 1, but you can get away with throwing away things in layer 4.
So the point here is that
but maybe
for an experiment, you have to commit to some, like, some algorithm of distribution, right? It's definitely a valid remark, and it's interesting to check and to explore whether there is a correlation. And yeah, I'm excited to look into this and see what this relates.
It makes me wonder whether the results of this sort of, you know, trade-off between this are highly dependent on the architecture of the model and the kinds of problems that you're trying to address. Because at least in this case, it looks like the first layers are very important, right? Whereas, at least in this case, the latter layers, you actually improved your performance by throwing away, by like sparsifying layer 4. Anyway, I think it does sound very interesting. So thank you for your comments.
It is something. Sorry, just a short remark about this. So something we have tried with a small model, with an MLP with 2 layers. There we did a whole scan along. So there are 2 weight matrices, and essentially we've considered possible sparsity combinations, like how much do I remove from the first layer and how much from the other layer. And there it was like the result was, of course, it's a very simplified setup, because the last, like the smaller layer is just the output layer, and it has only a few parameters, and it's easy to remove too much, so to say. But there it was also nicely visible that there is a certain range, like everything below 50% sparsity worked for the smaller layer, and for the larger layer, we could go like 90 something. That was the optimum where we would achieve the best result. So there, because the experiment is cheap and really easy to run, right? We could do like a whole grid scan. For the ResNet, becomes trickier. Okay, but there was more question. Yeah.
So I do a little bit of work with echo state networks and reservoir computers, and it's something that you saw where as the matrices became large, the error starts to increase, and something that shows up with echo state networks also when we initialize reservoirs. I was wondering, with regards to your sparsity and controlling different factors, if you consider controlling spectral radius in the matrices so that you're having contraction mappings, or avoiding like possible like bifurcation type behavior depending on your activation function, because that seems like in reservoir computing a lot of focus is kept on controlling the spectral radius of the reservoir matrix, which is kind of like a recurrent layer. And then also using graph theoretic initializations like Erdos-Renyi graphs and so on to try and get some kind of consistency in sparsity. Had you ever considered that? Thank you.
No, we have not looked into that. And this is, I must admit, this is new for me, because in terms of like standard neural networks for vision, I haven't heard about these terms. I do not think that it's at least not common to have this consideration. I'm very curious though about the sparsity in echo state networks and reservoir computing. So what exactly is sparse in that case? As far as I know, I haven't worked with it, but I'm just like roughly familiar with the setup. So you have random weights that are not being trained, that are being used as the reservoir, and then
they're randomly set to 0 to some percentage. And a lot of people like to initialize with, like I said, graph theoretic, like Erdos-Renyi and so on. But really, the key thing is that spectral radius on the matrices, because when the spectral radius is less than 1, the matrix becomes a contractive mapping, and it ends up being super important in having a good reservoir, which is basically an embedded dynamical system layer, nonlinear dynamical system that you use to map through. And so those 2 key points, I think, would be helpful for you to control different aspects of the experiments you're doing. One other thing I would mention is I'm out at UCSD, and there's a professor who, one of her works, she implemented a network that every so many steps resets the spectral radius if it starts getting above 1. And she got really good performance out of that for, it was some physics related application, like physics informed neural network application. So it ended up being key for her too. Thanks.
That's very interesting. Thank you very much. If you just want to request, if you could drop a link on chat, maybe, because I took some notes, but I'm not sure when I'll be able to find this when I Google. Maybe just like a reference, a couple of references. I'll be very curious.
Okay, I will do that. I don't know if I can do it right this minute, but maybe I can find your email and I'll just send it.
Okay. Okay. Thank you very much.
Okay. Thank you.
Other questions for Anna? I have a theoretical question while something comes in. Could you pull up your theory slide again?
Yes.
Yeah, thank you.
This one?
Yeah, that one. Yeah.
Okay.
So I was confused the first time I heard this talk why you called this the GP kernel. And the reason, I think, is because you only took derivatives with respect to the last layer parameters, right?
Yes. Yes.
So that's crucial. And that's one of the things that makes this much more like the GP kernel than the full NTK. But my question is, why did you guys only care about derivatives with respect to the last parameters here? Was it that it was more tractable, or was it more interesting for some reason? It
was essentially a simpler, cleaner computation. We did start out by considering the full NTK. And if I recall correctly, the result was actually very similar, but it was just way less cumbersome to show it for like GP and implement it. So we switched over to that. I see. So it was that you, I mean, basically to pass to the full NTK, you just add a term that's grad with respect to you also. Right. And if that term is either subleading or hard to compute, there's, so, okay. So it was practical reasons that you chose to study this rather than full NTK. Yes. Great. Yeah. Wonderful. All right. Any questions for Anna otherwise? In the meantime, I will drop the link on chat, which I mentioned before. Somebody was asking about the role, like in studying the depth. So I just pulled it up. I'm gonna drop it there. All right. Pulling it up myself. Any last questions for Anna? Don't be shy. You had a lot of questions throughout. It was great. I loved it, really. That was, yeah, one of the best seminars I've had, like with so much participation and really good, thoughtful questions. I've taken a bunch of notes for myself, so that's great. Very good. Yeah, it was a very nice seminar. All right, well, it seems that there are no more questions. So as always, I forgot to say that we should clap for you at the very end of your talk, but let's thank you. It was good to see everyone. Anna, thank you for the wonderful talk. It'll be posted on YouTube later if anyone wants to revisit Anna's talk. And I look forward to seeing you in person in Boston in the fall. So, cheers. Thank you. Bye.